In this video, we're going to review Lewis dot structures or electron dot structures, two names for the same thing, and then determining the molecular geometry, so its VSEPR shape. The shape of our molecules are really important in this course. In biochemistry, I guess just life in general, the shape of our molecule often dictates how it's going to react, what our products are going to be. So we need to become really good at being able to look at a molecule in two dimensions, right, on the screen or paper, and be able to visualize it in 3 dimensions, know what it looks like. So Lewis dot structures first. So Lewis or electron dot structures. And remember, our electron dot structures or Lewis structures do not tell us the shape. It only tells us how the valence electrons are arranged in that molecule. So it tells us how the valence electrons are distributed in the molecule. Essentially, it tells us what's connected to what and how they're connected. Do they have single bonds, double bonds, triple bonds? Are there lone pairs? That sort of thing. It doesn't tell us anything about the shape, however. So it does not tell us the 3-dimensional shape of the molecule. We need VSEPR theory for that. However, without knowing how the atoms are connected, we can't use VSEPR theory to determine the shape. So step 1 of determining the shape is, well, what is the actual just structure of the molecule? How are they connected? And I do have posted on Canvas a handout that I give my 151 students that has step-by-step directions for determining Lewis structures. Eventually in this class, you're not going to need that. Because we're studying carbon-based compounds and carbon is only going to form 4 bonds maximum, right? 8 electrons. If you need to go back and look at your quantum numbers, it's in the second, right? Its outermost electrons are in the second shell. So I only have s and p orbitals available, so a maximum of 8 electrons. So because of that, it is easier than it was in 151, right? In 151, we looked at things that had 10 or 12 electrons around it. Here, the max we're going to have is 8. So it becomes a little bit easier. I think you'll get pretty good at drawing carbon molecules that you don't need those instructions. But in the meantime, if you need them, I do have them posted on Canvas. I'm posting the handouts, by the way, on the practice problem page, and maybe I'll need to change the heading on that so it indicates handouts also. But if you go to the first module, and then you go to the practice problem page, I do have the handout posted there. And I imported one here so you can see those steps. But and we'll go through it kind of quickly. And I'm not going to spend a lot of time on Lewis structures just because, like I said, I assume you're pretty good at drawing it by now. But let's just go through these steps real quick. So, like I said, it's used to determine how the valence electrons, I'm just reading this one, how the valence electrons are shared. So the number of bonds, the number of lone pairs. Electrons are represented by dots, though I'm going to usually use lines. So a single bond is always composed of 2 electrons, so it could be 2 dots. I'm going to generally draw a line. Just remember that a single line is actually 2 electrons. We can have double bonds. Double bonds are just that. They're double, so 4 electrons, 2 lines. We can have a triple bond. A triple bond is literally triple, so 6 electrons or 3 lines. We can also have lone pairs or non-bonding pairs. It's 2 words for the same thing again. And those are going to be electrons, 2 electrons also, but no lines. Please never draw lines for lone pairs. Those always need to be dots. Only dots. So no lines, only dots. And then these are our step-by-step rules for being able to determine it. So I'm just going to go out and draw some, but please, if you have to go back and review these, go for it. You could print this out or have it open on a different screen and go through some examples. But your first step is to determine the total number of valence electrons. Do you guys remember the shortcut for doing that? If we use that AB numbering method for our groups, so if we use that for our main groups, the group number tells us the number of valence electrons. And that's not why. Like, carbon doesn't have 4 valence electrons because it's in group 4, right? Carbon doesn't consult the periodic table to determine how many electrons it should have in its outermost shell. But we can use a shortcut, right? We can use that as a tool to help us remember. So carbon's in group 4A. Again, we have to use the AB method. If you say 14, it doesn't work. So it's in group 4A. It has 4 valence electrons. And again, that's not why, but it's how we're going to remember it. Hydrogen's in group 1A, 1 valence electron. Nitrogen's in group 5A, 5 valence electrons. We're not going to be doing Lewis dot structures with things that aren't main groups, so it's pretty straightforward. Remember, if it's negatively charged, then you have to add an electron. Remember, electrons are negative, so if it's negatively charged, it has more electrons. If it's positive, you have to subtract one. And then determine how they're connected. I'm on step 2, connect them with a single bond. A couple rules. Remember, hydrogen can never, ever go in the middle, right? Hydrogen can never have more than 2 electrons, right? Its outermost electrons, and that's all it has, is one shell, is shell 1. There's only an s orbital, there's only one orientation, so 2 electrons maximum. Halogens generally don't go in the middle. It's just kind of a good place to start. And then generally the less electronegative atom goes in the middle, unless it's hydrogen, because hydrogen can never ever go in the middle of our molecule. Once you do that, right, just figure out how they're connected, connect them with single bonds. Then we're going to put lone pairs around the outside atoms until each has an octet, except for hydrogen, because remember, hydrogen can never have more than 2 electrons. If I have electrons left over, they go on the central atom. And then last step, if things that want an octet still don't have one, we had double or triple bonds. So things that don't want them, hydrogen, never more than 2. Boron's okay with only 6. It's actually neutral with 6 electrons. And then phosphorus and elements that are bigger can actually have more than 8, right? Their outermost electrons are in the 3rd shell. In the 3rd shell, I have d orbitals available, so I can have more than 8 electrons. So again, if you need these rules, they are posted for you. I'm going to go through kind of the really quick way to do it. The problem is the quick way often needs a little bit of experience, which you're going to get over the course of the semester. So maybe you'll be pulling out the rules now, and maybe you're just really good at Lewis structures, so it's not a problem. But eventually you'll just be able to draw them. So common atoms, right? We had carbon, and carbon's in group 4A, so it has 4 valence electrons. And if we remember back to high school or our 130 days, we think of it as having 4 sides, and we put 1 dot for it to have 4 electrons, and each electron is a dot, so 4 dots on each side. Right? I have 4 valence electrons. It wants 8. It wants to follow the octet rule. So 8 minus 4 means 4 bonds. Right? It has room for 4 more. It wants 4 more. Remember, these are all nonmetals, and we still haven't reviewed bonding, but they do form covalent bonds typically. And remember, covalent bonds, we're sharing electrons. So it's going to share 4 more electrons. It's not that it's going to take them, but it's going to share them. And this is for neutral. We're going to have a lot of atoms that aren't neutral. So this is ideal. We can do some examples where they're not, but this is for neutral bonding. Oxygen has, Actually, let's go in order. Nitrogen has 5 valence electrons. So you put one on each side and then you double them up. You don't even really need to do that. You just need to know that it has 5 valence electrons. It's in group 5A. That's how our shortcut for remembering it. It wants an octet, so it wants 8 electrons. So we subtract 5. That's 3 bonds, right? It wants 3 more electrons. It wants to share 3 more electrons. Oxygen, and since I started, we'll continue doing this, but you don't really have to. The important part is that it has 6 valence electrons. Again, oxygen wants 8, so 8 minus 6, it typically forms 2 bonds, right? It wants to share 2 more electrons. And halogens, they have 7 valence electrons. It also wants an octet, so 8 minus 7 is 1. It wants 1 more electron. It wants to share 1 more. And then hydrogen. Hydrogen has 1 valence electron. It does not want to form an octet, right? It only has an s orbital. There's only 1 value of m sub l for s orbitals, so 2 electrons maximum. So 2 minus 1, 1 bond, right? Wants 1 more electron. And phosphorus is right under nitrogen in the periodic table. Remember, atoms in the same group have similar properties. So phosphorus also has 5 valence electrons, 3 bonds. And then sulfur is right under oxygen. So also 6 valence electrons, wants 2 bonds, right? We could add that to it. Remember that phosphorus and sulfur, though, can have expanded octets. They can have more because they do have electrons in the 3rd shell. So I have d orbitals available. These are the ones that we're going to encounter most often, however. So since everything's going to have carbon, essentially you just need to be able to count to 4. And then not, like, don't disobey the octet rule and you'll be fine. So carbon wants typically 4 bonds, nitrogen 3, and then typically a lone pair, oxygen 2, and then typically 2 lone pairs, halogens 1, and then they would have 3 lone pairs, typically hydrogen 1 with no lone pairs. Again, this is for neutral. We will do some examples, and that's kind of one of the weirder things about organic when you're starting, is that we're so used to always obeying the octet rule that we think we have to all the time. We can't have more than 8. You can have less. You can have carbon that only has 3 bonds. It's not happy, and it's going to have a formal charge, but it's possible. I can't have carbon with 10, however. I don't have an orbital to put those electrons in. The orbitals that are above it, right, I'd have to go up another shell, are just too high in energy for it to be stable. So we can't go over 8 electrons for carbon, nitrogen, oxygen, and our halogens. We can't go over 2 electrons for hydrogen. Other than that, it's kind of just a puzzle piece deal. So let's do some examples. We'll start out pretty easy. And we'll just do CH4. So you can go through the rules, figure out the total number of valence electrons, and so on. I'm not going to do that. I'm just going to kind of build it. So I know carbon wants 4 bonds, and I know hydrogen can't go in the middle. So carbon has to go in the middle. Remember, each line represents 2 electrons. So I'm going to bond those 4 hydrogens around carbon. I can't do it any other way because I can't have hydrogens bonded to hydrogens, right? If I do this, this hydrogen in the middle has 4 electrons on it, and I can't do that. Never more than 2, right? Never, ever, ever more than 2. So this is my only option. If I count my number of electrons, carbon, remember we're sharing, so the bonding electrons belong to both atoms in the bond. So carbon has 2, 4, 6, 8. And then if we erase that, hydrogen, this hydrogen has 2, this hydrogen has 2, this hydrogen has 2, and this hydrogen has 2. So we've made all of those atoms happy. We could do C3H8. Again, hydrogen can't go in the middle, so I have no choice but to bond all 3 carbons together. And remember, Lewis doesn't tell us anything about the shape, so if I want to bond them together like this, I totally can. If I want to bond them together like this, I totally can. It doesn't matter, it just matters that the carbons are all bonded to each other, and then I'm going to put the hydrogens around it. Remember, if we go back up, each carbon wants 4 bonds, so I just need to count to 4. So the carbon on the left has 1 bond already, so I'm going to add another hydrogen for 2, that's 3, that's 4. The carbon in the middle has 2 bonds already, so I'm going to add 3 and 4. The carbon on the end has 1 bond, so 2, 3, and 4. And then if I count those hydrogens, it should be all 8. 1, 2, 3, 4, 5, 6, 7, 8. So that would be my structure. How about if we do C2, let's just do CH2O. This one's a little trickier. So again, hydrogen can't go in the middle. So now I have an option between carbon and oxygen. And one of those rules on that Lewis step sheet, or the steps for drawing Lewis structures, said that usually the less electronegative atom goes in the middle. So that's going to be carbon. We will review electronegativity if you don't remember that. So carbon's going to go in the middle, and then I'm going to attach the 2 hydrogens and the oxygen. And remember, you don't have to attach them. You don't have to attach them in the same orientation as mine. If I want to put oxygen here and a hydrogen here and a hydrogen here, that's perfectly fine as long as carbon's in the middle and it's bonded to those other atoms. Remember, Lewis structures don't tell me anything about the shape. So now I'm kind of looking at this, and it doesn't have a charge. My hydrogens are fine, but my carbon only has 1 bond. Sorry, my carbon only has 3 bonds. My oxygen only has 1 bond. Carbon wants 4, oxygen wants 2. So if I put a double bond between that, it gives me 4 for carbon. That double bond counts as 4 electrons. So I'm going to count it as 2 bonds, 1 double bond. And then oxygen gets its 2 bonds, right? It's 4 electrons. And then I put those 2 lone pairs on oxygen. And again, something like this at first might be a little trickier, but if you go through those steps on that handout in order, if you take them out of order, it doesn't work. But if you go in order, step by step, you will get this answer, I promise. You'll get the right answer. But eventually you'll be able to just throw that down without a whole lot of effort. A lot of times Lewis structures are already provided for us, and then it's just going from the structure to the molecular geometries, right, to its 3-dimensional shape. But there is occasion where we need to be able to draw the molecules out. So please practice this if you're a little rusty with Lewis structures. So let's talk about that shape next. So our molecular geometry, we're going to use VSEPR theory. So this is an acronym. It's valence shell, electron pair repulsion. So all capitalized, VSEPR theory. So valence shell, electron pair repulsion. So it's basically based on the fact that electron pairs repel each other. So we look at our Lewis structure, we see how many electron pairs we have. They want to get as far apart from each other as they can in 3-dimensional space, and then that's going to give us our shape. So this is used to determine the molecular geometry or shape of the molecule. And I do have a handout posted for this one too, which I'm going to pull up here in a minute. But kind of our first step is we need to draw the Lewis structure if it's not already drawn for us. Or electron dot structure, two names for the same thing. Our second one is we need to determine the number of electron groups. Depending on your instructor, for 151, you might have learned them as electron domains. I don't tend to use that term. I use electron groups more often, but an electron group and an electron domain are the same thing. And then from that, we determine the shape using the fact that those electron groups want to repel each other. So if I have two groups and they want to get as far apart from each other as they can, they're going to be 180 degrees apart. If I have three groups and they're trying to get as far apart from each other as they can, they're going to be like an equilateral triangle. They're going to have 120 degree bond angles. So determine the shape based on the electron groups repelling each other. And you can do that two different ways. One, you're just good at geometry and you can just visualize that. Two, you just memorize the table. Since organic only can have 80 electrons maximum, we are only going up to 4 electron groups, right? A single bond is 2 electrons. If I can have 80 electrons total, 8 divided by 2 is going to give me 4 groups. So it's a much smaller table than you would have had in 151. Right there, you would have gone up to 6 groups. So we're not going to have seesaw structures, square pyramidals, trigonal bipyramidal, none of those. So just up to tetrahedral. So I'm going to pull that handout up. Oops, sorry, it's marked up from a previous class. I should have stuff all ready for you. But again, it is posted on Canvas on the practice problem page. I'm actually going to be writing on this, so if you have access to a printer, it might actually be good to pause the video real quick, go print it out, and then you can write on it. If you don't have a printer, that's fine. We'll just take notes. Okay, so this top part we already talked about, right? Used to determine the three-dimensional shape, its molecular geometry, based on the fact that electron groups repel each other. First step is you need to know how they're connected, so draw the Lewis structure, and then we need to determine the number of electron groups. So a lone pair, a single bond, a double bond, and a triple bond, these are all one group each. One group each. So if I was to draw this molecule, that's a bad one, sorry. If I was to draw, let's actually do this one we did earlier. And we're looking at the central atom. I don't know that I have here. Yeah, I do, on the central atom. So I'm just looking at carbon, the one in the middle. I have a single bond, I have another single bond, and I have a double bond. So that's going to be 3 electron groups, right? Even though that double bond is 4 electrons, it's only in one spot, right? It's one group of charge, right? We want electron groups. So I have charge in 3 different spots. I have charge here, I have charge here, and I have charge here. So 3 electron groups. So lone pair, single bond, double bond, triple bond are one group each. And then the shape is just based on those 3 groups repelling each other. So this is the table that I had talked about, and I will reproduce it on the notes page. That way those that aren't printing aren't at a disadvantage. But we're just going to go up to 4. Sorry, I thought that was the highlighter. We're just going to go up to 4 electron groups. So 2, 3, and then 4. So a much smaller table than you would have had in 151. So I'm actually going to do it backwards. So I'm going to start with 4 because I want to start with carbon. So 4 electron groups. And it's easier for me to remember them if I group them together. So whether it's all bonds or 3 bonds in 1 lone pair or 2 bonds in 2 lone pair, it's still going to be 4 electron groups. I'm still going to have 4 things repelling each other in 3-dimensional space. So my basic structure, and I do have this drawn in the table in a box in the first column, is going to be tetrahedral. And it's really important that you guys are able to draw things in 3 dimensions. So if I gave you CH4, which has 4 electron groups, and you drew it without wedges and dashes, I'm going to give you 0 credit for it. So like I said before, the shape of our molecule is really important. We need to be able to draw that shape. So anytime I have 4 electron groups, it's going to be this basic structure. And I'm going to mark this up a little bit here. So essentially I'm going to have 2 in the plane. So those are flat. Nothing's coming out of the screen at you, nothing's going back. They're completely planar. And then this one that's wedged is coming out at you. So the world isn't planar, right? It's not 2-dimensional, it's 3-dimensional. So that is actually coming out at us. And then this one that's dashed is going back behind. And I can have my models when we do the video conference, so you can see it. But I do have 2 bonds in the plane, 1 coming out and then 1 going back is how we want to think of that. So everything in this group, everything that has 4 electron groups is going to have this basic structure. So if I have 4 bonds and then 0 lone pairs or non-bonding pairs. So my example for that was that methane molecule. Sorry, you don't know names yet, CH4. Right, that's going to have 4 electron groups, all bonds, all lone pairs. I'm going to take that basic structure, I'm going to put carbon in the middle, I'm going to go up to a hydrogen, I'm going to angle to a hydrogen. Now be careful, our bond angles, I haven't written it down yet, but if you have that table up, they're 109.5 degrees. So don't draw them 90, don't do that, that's 90. Don't do them 180, right? Do them somewhere in between. You don't have to get out a protractor and measure it, but you want to estimate 109.5. And then I'm going to have a wedge. So this is coming out at you. And then this dash means it's going back behind. So that would be my VSEPR shape, my molecular geometry for CH4. The name of it is tetrahedral. If you were to connect all those bonds, it forms a tetrahedron, the geometric figure. And my bond angle is 109.5 degrees. So all of them are 109.5. Again, we can look at models if you guys want to when we do our video conference. But all of those angles, that one, this one, this one, this one, this hydrogen around the back to that hydrogen, they're all 109.5. And you can label any of them. If I say label the bond angle, it doesn't matter which one because they're all the same. So that's our 4 bonds, right? We're still under a basic, no lone pairs. Another option, cylinder 4 electron groups, is 3 bonds, 1 lone electron pair, non-bonding pair. And I'm going to let's use nitrogen. I'm just going to do ammonia. So if I was to draw the Lewis dot structure for ammonia, sorry guys. I have lone pair and then 3 bonds. So nitrogen has its 3 bonds and its 1 lone pair. So again, it's going to be this basic structure, this one here. I'm going to put the nitrogen in the middle. 3 of my bonds are going to be to hydrogen, and then I'm going to have a lone pair. And it doesn't matter which position you put the lone pair in. I usually put it on top. You totally don't have to. It just has to be in one of those positions. So I'm going to put my lone pair here. I am going to draw my little orbital around it to remind myself that it does take up space. Most of the molecules we draw in here, I don't put the orbitals around lone pairs, but I do want us to have a good visual of it before I start being lazy on you. So that's going to be this guy. The name is based on just the atoms, just the bonds itself. So the name of this one is actually going to be trigonal pyramidal, because it forms like a little pyramid, and there's 3. So trigonal, pyramidal. And it is important to have both trigonal and pyramidal. If you just say trigonal, we actually have trigonal planar as a molecule. And then if you just say pyramidal, we're not going to see it in organic, but there are like square pyramidals and trigonal bipyramidal. So it's important to have both of those terms. I want to erase that highlighting, but I don't know if I can just erase the highlighting without totally ruining the whole thing. We'll find out. Yes, we can. My bond angle is actually going to be a little less than 109.5. So anything with this basic 4 electron group, my bond angle is going to be about 109.5. But every time you replace a bond with a lone pair, you actually make that bond angle a little bit smaller. Those lone pairs aren't constrained between 2 atoms. So like the electrons that are represented by this line right here are being pulled on by hydrogen's nucleus. They're also being pulled on by nitrogen's nucleus. These electrons are not being pulled on by another atom other than nitrogen, so it puffs out a little bit, it spreads out, and it actually squishes these guys closer to each other, making my bond angle less than 109.5. Be really careful to only label bond angles. This is one of my pet peeves. Let me get that bond back on and I'll show you. A bond angle is literally just that. It's the angle between bonds. It's not the angle between a bond and a lone pair of electrons. So if you were to label this as a bond angle, I am going to mark it wrong because you're incorrect, right? This here is not a bond. So this here is not a bond angle. So make sure when you're labeling bond angles that you're literally labeling bond angles and not something that's not, right? I want to know that you know what you're talking about, and if you're labeling that, you don't. So you have some options, but don't label between a bond and a lone pair. So less than 109.5 degrees. One more option here with the tetrahedral ones, and that's 2 bonds, 2 lone pair, and we can use water as our example. If we were to draw the Lewis dot structure for water, we would get something like this. And again, it's 4 electron groups total, so it's going to be this basic structure again. But in 2 of the spots, I'm going to have hydrogens, and in 2 of the spots, I'm going to have a lone pair. And it doesn't matter which. So oxygen in the middle, let's go up to a hydrogen, down to a hydrogen, and then I'm going to wedge the electron cloud. You kind of fill in the end a little bit, and then I'm going to dot this other electron cloud. It's going back behind. The other way might be easier. I could do a lone pair in the plane, this one in the plane, and then a hydrogen coming out at us, and then a hydrogen going back behind the board. Or not board, old habits, back behind the screen, back behind my iPad. The name again is just based on the atoms. So I have 3 things. They're not in a straight line, they are bent. So that is the name of these. Angular is also correct. And then my bond angle, again, make sure you label a bond angle when you're labeling a bond angle, less than 109.5. degrees. So again, all of these are based on that tetrahedral structure, right? This basic structure, and in this case, I have bonds in all of my spots. This one, my Ammonia is also based on that, right? Sorry, this is getting messy when I hurry. But what I did is I took this one, oops, not both of them, just the top one, and I put a lone pair there, so my little pyramid. And then this one, right, basic tetrahedral structure. See if I can erase just what I want. And I did that, so bent. So the easiest way I think to remember him is to just remember this for 4 groups. And do I have an atom in all 4 spots, plus the middle, of course? Do I have an atom in just 3 of the spots, plus the center? Or do I just have it in 2 of the spots? So tetrahedral, trigonal, pyramidal, and then bent or angular. You can also, by the way, and I usually do it one of 2 ways. I'm going to draw that basic tetrahedral structure again. Like I said, you have to have 2 in the plane, roughly at 109.5 degrees. My bond angle there is probably a little too big. And then 1 coming out, 1 going back. The 2 in the plane don't have to be up and to the left. You could draw the 2 in the plane like this, and then the one that's going out over here if you wanted, and then the one that's going back, that's fine. I'm really bad at drawing this upside down, but I'm going to give it a shot. I could draw those as the ones that are in the plane. I'd have my wedge, and then my one that's going back. That's fine. Any of those are fine. I tend to do the one that I did originally and then this one. I don't do them upside down very often, even though that turned out pretty good this time. So, you know, again, it doesn't really matter. It just has to be those sort of shapes. So 2 in the plane, 109.5. This one here is too big. And then one coming out, that's our wedge. That's messy as I'll get out. And then one going back, that's my dash. So 3 electron groups. And I'm going to do the same thing. I'm going to do a basic structure just like we did up here with our 4 groups. So I have 3 electron groups repelling each other. So these guys are going to be trigonal planar. I want to try to draw it so it's nice. So this is going to be my basic structure. I'm going to have 120 degree bond angles and then the basic trigonal planar. So it's flat, right? Trigonal planar, not pyramidal. So nothing's coming out at us, nothing's going back behind, so just 2 dimensions. And we can have 3 bonds, 0 lone pair. And we can use this example we did before. Where I had the carbon in the middle with the hydrogens, and then the 1 double bond. So that would be 3 electron groups. No lone pairs on this central atom. There are lone pairs on oxygen, but that's not going to affect the shape of carbon. So I'm going to have carbon in the middle. And if I go back to this basic shape over here, I can put the oxygen in any of those 3 spots. I'm going to pick the top, but again, it could go in any of those spots. And then I'm going to angle those down to hydrogen. So trigonal planar. And then my bond angles are going to be 120 degrees. And I could label, you know, that's 120 and that's also 120. So any of those 3. My other option, 2 bonds and 1 lone electron pair. And we could do ozone. Ozone actually has formal charge. We'll review that in our next video, but I do have formal charge on there. But if I look at my central atom, right, the one in the middle, that oxygen has a single bond, a double bond, and then a lone pair. So that's 3 groups. 2 of them are bonds, the single and the double, and then 1 lone pair. So same sort of idea. I'm going to go back up to this trigonal planar structure. I'm going to put the lone pair in one of those 3 spots. It doesn't matter which. So the middle oxygen in the middle, I'm going to put the lone pair on the top. Again, eventually I stop drawing those electron clouds, but it is good while you're learning or refreshing your learning. And then I'm going to put my charges on here. We will review formal charge. So this is going to be my shape of this guy. And then just like we did with the other ones, the tetrahedrals that had lone pairs, the name is based just on the atoms themselves. So this one is going to be bent or angular. And then my bond angle, only one place to label it this time, less than 120. Right? Anytime we have a lone pair, it's going to take up more space than a bond is, and it's going to compress those bonds closer to each other. Again, don't do this, right? Don't label that as a bond angle. That's not a bond angle. And then one more, and that's 2 electron groups. And only one option for this one. This one's just going to be linear. So what can we use? Let's use carbon dioxide as our example. So the carbon in the middle has 2 bonds. It's not going to have any lone pairs. Right, both of those bonds are double bonds, but they're double. And I already drew this one with its shape. If you have 2 things trying to get as far apart from each other as they can, they're going to be straight out across from each other, so 180 degrees. And then the name of it, it's just in a straight line, so linear. And that's all of them for us, so much shorter than it was in 151. So 4 electron groups. Again, all of them based on, this stuff is going to be highlighted so much, all of them based on this tetrahedral structure. Right, 2 in the plane, 1 coming out, 1 going back. The wedge is coming out, the dash is going back. 3 of them are all this trigonal planar structure, so nothing coming out at us, nothing going back, completely flat, right, just 2-dimensional. And then my 2 electron groups, only 1 option, and that's just going to be linear, so straight out. So please, if you're rusty on these, do some homework problems, spend some time looking at that table, maybe rewrite your notes a little bit. Again, looking at a molecule that I give you and visualizing the shape really needs to be something that becomes second nature for you in this class.